All right, this is just a quick overview of conservation of energy, specifically for my online students. Um, what we have learned about is kinetic energy, and the equation for that is 1/2 mv squared. And that has to do with the energy that is related to an object's motion. We have also learned about potential energy due to gravity, and that has to do with the object's location. If it's off the ground, some vertical height, it has potential energy due to gravity. We have also learned about the potential energy that could be stored in a spring, and that is related to how far the spring has been compressed or stretched. In order to, again, um, understand how the potential energies are obtained, we have to do work in order to do that, and that in order to generate that potential energy, and potential energy is stored energy. So when we do this work, energy is transformed from one form to the other. So kinetic energy gets transformed into potential energy. So for example, something is moving and slides up a hill, kinetic energy can be turned into electrical potential energy, like hydroelectric plants, like a dam, for example. We can have a spring, and that potential energy in the spring is converted into kinetic energy, like a dart gun. Okay. No matter what we do, the energy in the universe remains the same. This is what we mean when we say energy is conserved. Okay. It is never canceled or deleted, so to speak. We are always transferring it from one form to the other. So, what do we mean by conservation of energy? Mechanical energy, let's say initial at some point, has to be equal to the mechanical energy final. What is in mechanical energy? Well, the types of energies that we have learned: kinetic energy, potential energy due to gravity. Maybe we have a spring in the problem, so we have a spring, and then we'll give a little subscript I for the initial location, and we will set it equal to the kinetic energy final plus the potential energy due to gravity final plus the potential energy due to a spring final. But at all times, if energy is conserved, we will have those two quantities equal to one another. So this is what the slide shows. The sum of the kinetic energy, potential energies of the object is referred to its mechanical energy. And that is what we have here. And they will equal each other if we have conservation of energy, okay? Conservation of energy. Um, we have this when there is no work being added, no work um, being done on the system. Okay. Now, if I have work, like example, friction, then we will lose this energy in the form of heat. Okay. Or let's pretend I have a motor that's involved and I am going to add energy, then we gain energy. So we will have the exact same situation: kinetic energy plus potential energy due to gravity, potential energy due to a spring. Initial is equal to all those energy final, and then we have to add the amount of work that we have added to that system. This can be negative in the case of friction, example. Friction is present, so we lose energy due to friction, or this can be positive. Someone has a motor or some type of rocket propelling. Okay, so it can be positive or negative. All right, so we can solve many physics problems using conservation of energy. So, for example, this picture shows a key person holding a key, and they have essentially the only, if it's at rest, the only type of energy that you notice that they have stated here is potential energy due to gravity. And as it falls, As it falls, that potential energy due to gravity is then getting converted to kinetic energy. And now at the bottom, it has no potential energy due to gravity. What about somewhere in the middle? In this location, I'm going to have both potential energy due to gravity plus kinetic energy. And this total will equal the energy that I started out with. Okay. This total will always stay the same if there's no work. Okay. So we can actually solve for different things depending on what we're asking for. The conservation of energy means that objects moving downward through the same vertical distance but following different paths will have the same final speed. So what does that mean by this? So this person slides down this slide, this person slides down this slide, and if there is no friction on both slides, then no matter what, if they have started at the same height, they both start off with the same potential energy due to gravity. And at the bottom, they're going to end up with the same kinetic energy. And assuming they have the same mass, actually, the masses won't matter. They will end up with the same speed. Okay, and you can see that here. Okay, how do I know the masses don't matter? This is something that people struggle with sometimes. Potential energy due to gravity initial has to equal that kinetic energy final, and this is mgh initial equals 1/2 the mass times v final squared. Notice that the mass cancels and that final velocity will end up the same thing. Okay. All right, so here's another example. I encourage you, this is in your OneNote, to take a look at this example. It actually gives you a good practice problem. So we have a snowboarder coast on a smooth track that rises from one level to the other. The snowboarder's initial speed is 4 meters per second, and it makes it to the upper level and comes to rest. Okay. And then with a slightly greater initial speed, as in case two, it's still moving to the right at the upper level. What is its final speed in case two? Okay. So they calculate some things here. We calculate the initial kinetic energy in case one. We calculate the initial kinetic energy in case two. We find the amount of energy in case two that we had extra. We had additional amount of energy, and that will end up in the final kinetic energy for case two, and we can calculate the speed. Okay. Because we didn't know the height, and that is the reason why we were able to do that. All right. Okay. So let's see. That's what I have for us. We are still working in class. In class assignments, we are currently working on. Uh-oh, I don't have it in here. Oh, it's here. Um, uh, Oh, come on, I'm getting there. There it is. 7.1, we are working on conservation of energy problems 38, 39, 44, and 45. I will put a solutions video for those as well.